Hi, I'm Bob. Let's continue to solve the problems from 6 to 13 for Chapter 4, Multiple Regression Analysis, Inference of the textbook Introductory Econometrics, a Modern Approach, the 7th edition. Here's problem number 7. The first question is to compare the estimates using the entire sample of 43 firms to the estimates from a subsample of 29 non-unionized firms. First, the t-statistic for the whole sample is 0.042 divided by 0.019, which is 2.21. The 5% critical value against a two-sided alternative with 39 degrees of freedom is 2.02. The t-statistic is above the critical value. Using the entire sample, the effect of job training becomes statistically significant at the 5% level against a two-sided alternative. By contrast, the effect is not significantly different from zero at any conventional level using only the 29 non-unionized firms. Second, the job training effect on the scrap rates is larger using the entire sample. 1 more hour of training per employee lowers the scrap rate by 4.2% on average, while it is 2.9% in the subsample of the non-unionized firms. The second question is to rearrange the variables. We can rewrite the population model as follows. The new parameter theta 3 is the sum of beta 2 and beta 3. The null hypothesis theta 3 equals 0 means the number of employees has no effect on the scrap rates after holding training hours per employee and sales per employee fixed. The answer is no to the third question. Controlling for worker training and the sales to employee ratio, the estimated coefficient on the size of firms is not statistically significant at any conventional level. The t-statistic is 0.2. The 10% critical value against a two-sided alternative with 39 degrees of freedom is 1.684. Since the t-statistic is below the critical value, we could not reject the null hypothesis that theta 3 is 0. In other words, the size of the firm has no statistically significant effect on the scrap rates. For the fourth question, the null hypothesis is that beta 2 equals -1, and the alternative hypothesis is that beta 2 does not equal -1. The t-statistic is equal to the estimate of beta 2 minus the hypothesized value, and then divided by the standard error of the estimate. It is very small, 0.132. The 10% critical value against the two-sided alternative with 39 degrees of freedom is 1.684. Since the t-statistic is below the critical value, we could not reject the null hypothesis that a 1% increase in the sales-to-employee ratio is associated with a 1% drop in the scrap rate at the 10% level. We could also compute the p-value for the t-statistic. It is 0.896, which suggests that we could not reject the null hypothesis even at the 85% level. Let's go to the eighth problem. The first question is to derive the variance and the standard error of a linear combination of the parameters. They are as follows. The second question is to write the t-statistic for the test. The third question is to rearrange the equation and define a new parameter, theta 1, to represent the linear combination, beta 1 minus 3 times beta 2. Then we can regress y on x1, 3 times x1 plus x2, and x3. We can directly obtain the estimate of theta 1 and its standard error. Let's find the answer to problem number 9. The first question is to do the t-test for individual variables. For the variable education, the null hypothesis is that its coefficient is 0, and the alternative is that it is not 0. The t-statistic equals minus 1.893. The 5% critical value against a two-sided alternative with 702 degrees of freedom is 1.960. Because the t-statistic is below the critical value, we fail to reject the null hypothesis that the coefficient is 0. Similarly, we can calculate the t-statistic for the variable age. It is also below the 5% critical value against a two-sided alternative with 702 degrees of freedom, 1.960. So we could not reject the null hypothesis either. Therefore, the answer to this question is no. Neither education nor age is significant at the 5% level against a two-sided alternative. The second question is about the R-squared form of the F statistics. We have the R-squared for the long unrestricted model, 0.113, and R-squared for the short restricted model, 0.103. The null hypothesis is that both coefficients on education and age are 0. The number of restrictions is 2. The number of degrees of freedom of the unrestricted model is 702. Plug in all the elements and we have the F statistic equal to 3.957. From the F distribution table, the 5% critical value with 2 and 702 degrees of freedom is 3.00. The F statistic is above the critical value, so we reject the null hypothesis, and we can conclude that education and age are jointly statistically significant at the 5% level. For the third question, including education and age in the model does not greatly affect the estimated trade-off between sleeping and working. The estimate changes slightly from minus 0.151 to minus 0.148. For the last question, heteroscedasticity violates the homoscedasticity assumption. The t-test and the f-test are no longer valid because the t-statistics and the f-statistics do not have the t-distribution and the f-distribution under the null hypothesis if the classical linear model assumptions are not satisfied. Let's go to the 10th problem. The first question is about the F statistic for the overall significance of a regression. The null hypothesis is that all the parameters are 0. We use the R-squared form of the F statistic. The numerator is the R-squared of the model divided by the number of restrictions, which is equal to the number of all parameters in the model, k. The denominator is 1 minus R squared, and then divided by the model's degrees of freedom. We plug in all the elements and have the F statistic equal to 1.409. From the F distribution table, the 5% critical value with 4 and 137 degrees of freedom is 2.45. Because the F statistic is below the critical value, we fail to reject the null hypothesis that all the explanatory variables are not jointly significant at the 5% level. The second question is to re-estimate the model using the log form for net income and CEO salary, and redo the F-test and T-test. The F statistic is 1.169, lower than the critical value. So we fail to reject the null hypothesis at the 5% level again. No explanatory variable is individually significant at the 10% level either. The conclusions do not change. For the third question, since some values of the variables DKR and EPS are 0 or negative, using the log form will lose some observations. There's no reason to exclude some firms from the model. We should not use the log forms for those two variables. The fourth question is about the evidence of the efficient markets hypothesis. According to the above estimates, the evidence for the predictability of stock returns is weak. The 4 explanatory variables are jointly insignificant at the 5% level. No explanatory variable is individually significant at the 10% level. The explanatory variables do not have significant effects on the stock returns. We also find a very low R-squared. Less than 4% of the variation in the stock returns is explained by the variation in the 4 explanatory variables. Let's solve problem number 11. The first question is about the effect of the firm's profit on the CEO's salary. From the table's last 2 columns, the estimates of the profit effect are not statistically significant at any conventional level. The t-statistics are around minus 1.05. The 10% critical value against a two-sided alternative with 171 degrees of freedom is 1.645. Because the absolute value of the t-statistic is below the critical value, we fail to reject the null hypothesis that the firm's profit has no effect on the CEO's salary after controlling for the other explanatory variables. The second question concerns the firm's market value's effect on the CEO's salary. Model 2 gives an estimate of 0.112, and the t-statistic is 2.24. The 5% critical value against a two-sided alternative with 173 degrees of freedom is 1.96. Because the t-statistic is above the critical value, we reject the null hypothesis. We can conclude that the firm's market value has a statistically significant effect on the CEO's salary at the 5% level. As the firm's market value increases by 1%, the CEO's salary is estimated to increase by around 0.1% on average. Notice that the p-value of the t-statistic is 0.026, which implies that the effect is significant at the 5% level, but not at the 1% level. Model 3 gives a similar result. The third question is to interpret the coefficients on the years as CEO and the years with the company. The CEO tenure variable is statistically significant at the 1% level because the t-statistic is 3.11 and the 1% critical value against the two-sided alternative with 171 degrees of freedom is 2.576. The t-statistic is above the critical value. We reject the null hypothesis at the 1% significance level. And we can conclude that one more year as CEO increases the CEO's salary by 1.7% on average, holding other variables constant. For the coefficient on the years with the company, its t-statistic is minus 2.79. Its absolute value is also above the critical value, so we reject the null hypothesis at the 1% level against a two-sided alternative. We can conclude that one more year with the company decreases the CEO's salary by 0.9% on average, holding the years as CEO and other factors fixed. In other words, the years with the company, not as a CEO, reduce salary. Both explanatory variables are statistically significant at the 1% level. We have just answered the last question. Since we have controlled for the years as CEO, It makes sense that the years with the company, not as a CEO, reduce the CEO's salary. Let's go to the 12th problem. The first question is to interpret the coefficient on the log expenditures per student. If the expenditures per student increase by 10%, the math test pass rate is estimated to increase by 1.116 percentage points. 11.16 times 0.1 equals 1.116. The minimum value of log expenditures is 8.11, so the lowest pass rate is 21.17 percentage points. It is still positive. There's no problem with a negative intercept. The second question concerns the R-squared. The R-squared is 0.0297. About 3% of the variation in the math test pass rates is explained by the variation in the log expenditures per student. A low R-squared does not suggest omitted variables in the model. Generally speaking, more explanatory variables in the model lead to a higher R-squared. A random assignment ensures that the expenditures per student are independent of the error term, which implies that the zero conditional mean assumption holds, and the estimate is unbiased, but it does not necessarily increase the R-squared. The third question is to compare the estimate in the multiple regression to the estimate in the simple regression. When the log of enrollment and percent of students eligible for the federal free lunch program are included, the coefficient on the log of expenditures per student reduces from 11.16 to 7.75. The t-statistic is 20549. The 1% critical value against a two-sided alternative with 404 degrees of freedom is 2.576, and the 5% critical value is 1.960. The spending coefficient is still statistically different from 0 at the 5% level, but not at the 1% level. For the fourth question, adding two more explanatory variables to the model, the R-squared becomes higher. The enrollment and the free lunch program variables help explain the math test pass rates. There were other factors that could be used to explain the pass rates. For example, the teacher-student ratio, the student's average family income, and the student's family structure are the variables that can explain the pass rate. Let's solve the last problem. In the first question, as the number of students not living with both parents increases by 10%, the math test pass rate will decrease by 8.33 percentage points. It is statistically significant at the 1% level. When the percentage of students eligible for the federal free lunch program is added as an explanatory variable, the family structure effect drops to 0.275. The t-statistic is minus 2.34. The p-value is 0.020. The effect is statistically significant at the 5% level, but not at the 1% level. The second question concerns the expenditure per student. The t-statistic is 2.23, and the p-value is 0.027. It is statistically significant at the 5% level. This is a level log model. If the expenditure per student increases by 10%, the math test pass rate is estimated to increase by 0.9 percentage points. It is not an economically large effect. For the last question, I will choose the last model. I will not choose the first two models because they suffer from the omitted variable bias. The expenditure per student is an important factor behind the pass rate, and it is statistically significant at the 5% level. It should be included in the model. Comparing the last two models, we find that the median income variable is not significant at any conventional level. The R-squared does not improve with it. The disadvantage of including it is that it is correlated with the family structure variable, and therefore the standard error of the percent of students not living with both parents becomes larger. The t-statistic becomes smaller, and the effect becomes less significant. The p-value changes from 0.027 to 0.089. The family structure effect is significant at the 5% level in the last model, but not in the third model. So, the last model is the best choice. Using the last model, the 95% confidence interval of the estimate is from minus 0.489 to minus 0.029. Thank you very much for solving the problems with me. See you soon. Thank you for watching this video and subscribing to my YouTube channel. See you next time.